Dear colleagues, I am here to present to you an application of uncertainty quantification methods. It is not so creative in terms of uncertainty quantification itself, but is interesting as application. It's a joint work of some colleagues of Germany and Brazil, and France, which are specialized in telecommunications. It concerns a system that is called the MIMO, multiple input multi-output system, where you have antennas which transmit to a receiver. A signal is sent, and the message consists in a sequence of symbols chosen in a given alphabet of a given length M. In general, the alphabet is complex. The receiver receives a message which is modified by the transmission and by a noise. The standard model is the channel model, where the transmission is given by a linear matrix 8 and a noise n. And the single available data is what is measured by the receiver. In some situations, you may know also the message. You can rewrite it in terms of real and imaginary parts. Okay, it is classical. And then you can try to determine the distribution of the noise. And how? You can send a new message. This is called a silent mode. No message is sent, so what you have is just noise. You can measure it, and from the measurements you can apply the classical methods from uncertainty quantification to represent the noise using a random variable, and from this representation you can use it for deduce some things like the mean or the variance of the noise. As an example, consider a MIMO system with 8 transmitters, 8 receivers. You take 250 measurements of the noise. We assume that in the real part the noise is uniform, and in the imaginary part it is Laplace distributed. And as you don't know it, you use a Gaussian U to fit the noise. Well, what is the result? Is like this. It works because this is a classical feature in uncertainty quantification. It's nothing of new here. Here you have an example of the evaluations of the mean and the real part and the imaginary part. Here you consider the real part uniformly distributed with a mean minus 0.03, and the imaginary part Laplace distributed with a mean 0.02. And these are the results obtained after 250 measurements. Here you have the PDF of the error. When you generate a sample of 10,000 variates using the representation determined with 250 measurements. And you observe that the mean of the error in the real part is this one, and the error in the imaginary part is this one. Okay. Now, to identify the channel matrix, if you have the noise, you send a null message. You receive the message, you find the distribution, estimate the mean, take the mean of the noise off, and then with the rest you determine 8. The null message in general is formed by reference signals called the pilots, but you can choose the pilots. It is determined by the user. Thus you can take the estimations by using several methods. But maybe the simplest method is the estimator tool when you send messages which corresponds to the classical bases 10001000001 and so on. So each message leads you to the determination of one of the columns of the matrix 8. You can apply this method and then you have the percent of these errors which are distributed like this. As you can see, the mean error is about 25% and in the real part and in the imaginary part by 3-2% with a small standard deviation. And if you use the second approach, well, you have analogously, you have these results which are of the same order. So both the methods are equivalent. Now, if you really want to read the message, you know the noise, you know the channel matrix, and I send you a message and you want to read it. Okay? Messages are generally sequences of symbols, and the symbols are in general made by alphabets which are of this kind, separated by a spread of 2 between consecutive symbols and with a given length. In general, they are symmetric. The first step is to transform each symbol into a binary chain by taking just a matrix which is a diagonal matrix, identity matrix. Okay, so a symbol is a line of the identity matrix, and what you want is to find what is the line. You can transform the problem. The important is that now you have an unknown, it's z bar, which is a vector of unknowns to be determined. And it satisfies conditions, nonlinear conditions, because you want that the symbols, recall that z bar is a matrix in a part of identity matrix. So you have a line which a single element which is 1, all the other elements are 0. And you can rewrite this under the form below, which corresponds to nonlinear constraints. So you can try to use nonlinear least squares. You have a simplified approach, which is much more simple, where you have directly, without no least square solution, the answer. Well, in both the case, when you have the vector x, you have still some errors. So you determine what is the symbol which is the closest one to the value of xi. Here you have an example with a message of alphabet of length 2, 1 minus 1, and the number of errors in the detection. The number of errors is here, is in the horizontal line, and in the vertical line you have how many tests belong to class. Okay, let's come back. And in here you have another example with another alphabet of length 8. So it is minus 7 to 7. Now again, you observe that the 0 errors is large number, but when the length of the alphabet increases, you have more difficulty because you solve a larger least squares problem. Here we have for a 32 length alphabet, so we observe that the simplified method is now not so good. It's bad. The results are not good. You have many tests where 3, 4, 5, 6 errors in a message of this size. Okay. In an alphabet of 128 symbols method to completely fast. How to improve the results? Well, a simple way is to increase the spread. If the distance between consecutive symbols is larger, you can expect that it is easier to detect them, to separate them. Indeed, if you consider method 1 and method 2 with a spread of 4 and an alphabet of length 8, you have in method 1 practically all the results correct, and in method 2 a very large number of tests with all the results correct. Again, if you increase the size of the alphabet, you need to increase the spread because it becomes more difficult. Here you have a spread of 8, and now method 2 fails, while method 1 is still good. And to analyze the influence of a spread, you can get this kind of test where you observe that if the spread increases, the quality of the results increase for both the approaches. Another way to improve the result is to use redundancy. If you send the same message several times, you can then evaluate a mean of the results and use it as the real message. So you observe here that if you send the messages more than one time, also the performance increases in both the methods. And what is more influent? Okay, let us try to see here. We observe that it is analogous. If you send more messages or if you increase the spread, you have all this behavior is very similar. Here for 128 alphabet length, though you observe analogous results. As a conclusion, we say that the UK approach is able to furnish the distribution of the noise, to identify the channel matrix, and to detect the symbols, so to read the messages. And the UK approach has the advantage of dealing with non-Gaussian noise and the noises that have non-zero mean. The results may be improved with redundancy and spread. We tested if up to 128 elements, and to be more conclusive, this approach must be compared to the classical detection methods, and it is interesting to note that it can be extended to the dynamic estimation of the error rate, what is in fact one of the criteria of the recalibration of the telecommunication systems. When the error rate attains some value, some threshold, then you must recalibrate. And this method may be used to this. Thank you.